Welcome to video 5-1, History of the Periodic Table and Periodic Trends. So, Chapter 5, we're looking at something called the Periodic Law. Okay, so, first thing, really quick, history of the Periodic Table. Okay. In 1860, this was the first time that the International Congress of Chemists actually got together and they met. Okay. So, a guy named Cannizzaro introduced a method for accurately measuring relative masses of atoms. So now people could actually start agreeing on what was the atomic mass of an atom, and also for new elements, what was a good way to determine their atomic masses. Okay. In 1869, Mendeleev put together his periodic table of elements. Okay. Now, prior to this, other people were trying to group elements according to properties, okay? And other people did things similar to what he did. Okay? He arranged his elements by similar properties. So did a bunch of other people. But the problem was when they were doing this, a lot of elements ended up being in columns that were not similar to themselves. Okay? So he said, well, I'm going to arrange my elements by increasing atomic mass, because now they had a way to measure the atomic masses. Okay. Other people were doing that too, but that was when they're running into discrepancies. So what he said, what made his periodic table unique, was that he said, you know what? An element probably should go here, okay, but I'm not going to put it here. I'm going to put it over here and leave this space blank. Okay, so he ended up seeing that there were some deviations in atomic mass though when he did that. Okay, and basically he said, well, since this element doesn't go there, there's nothing here. Why? Because there's an element we haven't discovered yet. Okay, so his table left these blank spaces. Okay, now in 1911, Moseley was trying to figure out, okay, well, why did we have deviations in the atomic mass? Why is it sometimes as you went left to right, the masses got larger in general, but there are a couple places where when you went to right, you went from left to right, an element right next to it actually got smaller in mass. And he determined that, well, if you arrange it by increasing nuclear charge, which is basically the number of protons, the atomic number, then it would fit Mendeleev's table perfectly. Okay, so periodic trends. First of all, what is a periodic trend? Well, if something is periodic, that means it repeats itself after a certain interval. This interval is what we call a period. Okay, and on the periodic table, you know that the periods are rows. So a periodic trend is something that changes as you move left to right across a row, but when you drop back down to the next row, the trend repeats itself. Okay, so some really common and simple periodic trends. The atomic number. As you move left to right, it gets bigger. You start out with metals, you turn into metalloids, and then you end up with nonmetals. Okay, drop down to the next row, same thing happens. Atomic number gets bigger, you start out with a metal here, and you end up with a nonmetal on the right side. Okay, so the trends that you guys are responsible for knowing. Okay, all the important ones are related to the trend in the atomic radius. Okay, now, how do you figure out the atomic radius? Okay, well, kind of hard if you think about it, because remember, we know that we have a nucleus here. Okay, and outside of it, we have our electrons. Okay, now, little problem. Do we know exactly where those electrons are located? Remember, these are in orbitals. Orbitals are just spaces or regions. So, if we don't know where the electron's located, how can you measure the distance from here to where the electrons are? Okay, well, what they did instead is they said, well, we'll define it as half the distance between the nuclei of identical atoms that are bonded together. So instead, what they said was, well, you take a nucleus like that, and you bond it to another atom that's identical, and you measure the distance from one nucleus to the other nucleus, and then you take half of it, and that will be the radius. Okay, now, what do you think should happen when you go from left to right? Will the atomic radius as you move across the row? Okay, so probably a good idea, get out a periodic table right now, okay, one that has elements in it, and we'll start looking at some of the trends. So as you move left to right, do you think that the radius should get bigger, smaller, or it should stay the same? Okay, well, take a look at what actually happens. As we go left to right, the atoms start out large, and then they get smaller. Now, is that what you expected? Okay, moving left to right, the atomic radii decrease. Okay, and some of you may be thinking, well, why is that? As I went left to right, we added more electrons. Okay, we also added more protons, but the protons go in the nucleus, so that shouldn't change the size or the radius of the atom. You add more electrons, shouldn't the atom get bigger? Okay, so it actually gets smaller. Now, why is that? Okay, well, as the atom gains more protons, those go in the nucleus, doesn't make the atom bigger, but it makes the attraction, the attractive force between the nucleus and the electrons stronger. Okay, and also, as you put in more electrons, they don't go farther away. They go into the same energy level. Remember, everything in row 2, electrons are all in energy level 2. Anything in row 3, electrons are in energy level 3. So, you don't get extra shielding from the nucleus. Okay, so let's say this is one energy level, one set of electrons. This element right here has 2 sets of energy levels. This one has 1, 2, 3. Okay, think of these as like walls, and think of your nucleus as like a wireless hub or something for your computer. Okay, the more walls it has to go through, the weaker the signal is going to be. So the weaker the attractive force is going to be. Okay, but as long as you go along the same row, you don't add any extra energy levels. Okay, now moving down, atomic radii will increase, and this should be simple because don't forget, every time you drop down one more row, you add one more energy level. Okay, and because you're adding more energy levels, there's more shielding from the nucleus. It's like your signal, your attractive force has to go through more walls. Okay, now, remember this. Large atoms will easily lose electrons. Okay, the reason why they're large is you have weak attractions between the nucleus. Small atoms will easily gain electrons. Okay, reason why they're small is because they have a strong attractive force between the nucleus and the valence electrons. Okay, so you can pause the video, take a look at these elements, take your guess, and then restart it. Okay, so find these elements on your periodic table: sodium, chlorine, phosphorus, and argon. Which one should be the smallest? Okay, pause, make your guess, and then come back. Okay, correct answer is argon. Okay, hydrogen, fluorine, bromine, rubidium. Which one should have the largest? Okay, again, pause the video, find your elements, come back, and check. Okay, rubidium should be the largest. Okay, our next periodic trend, and remember, everything goes back towards atomic radius trend. Okay, ionization energy. Now, first of all, you need to know what ionization energy is. Okay. Ionization energy, energy needed to remove an electron or electrons from an atom. In other words, you create cations. Okay, now, as we move left to right, should it become easier or harder to remove an electron? Okay, if it becomes harder, that means the larger ionization energy must be. Okay, and the general trend as we move left to right, don't forget, we got big atoms and we got small atoms on this side. Okay, so which one is it harder to remove the electrons from? Okay, the big or the small? Well, the smaller atoms become harder to remove an electron. So on this side, you're going to have small ionization energies, and on this side, you're going to have large ionization energies. Okay, and going down, it decreases because when you go down a row, the atoms get larger. The larger the atom, the smaller or easier it is to remove the electrons. So a smaller amount of energy you have to add to it. Okay, now, which of these will have the smallest ionization energy? Again, find these elements on your periodic table. Okay, pause the video, figure out which one, and come back and check your answer. Okay, what are you looking for? Since you're looking for the smallest ionization energy, are you looking for the largest atom or the smallest atom? Okay, and cesium. Why cesium? This one right here, this is the largest atom, okay, or largest radius. Okay, now, the second ionization energy. This is the amount of energy to remove a second electron. Okay, and you're not removing it from an atom anymore. You're removing it from a +1 ion. Okay, why? Because once you take out one electron, you create a +1 ion. Okay, so now when you're taking out another electron, it gets harder. Okay, so it's always going to be larger than the first, because you're trying to remove an electron from a cation, okay, which now has more protons than electrons, so there is a stronger attraction between the nucleus and the electron, so it's harder to pull out another electron. Okay, now you get really large jumps if you're moving an electron from an ion that has reached a noble gas configuration. Okay, because now these are really stable, and it's really hard to remove an electron. Okay, so which of these will have the largest second ionization energy? Okay, so again, find these, pause the video, and figure out which one should have the largest second ionization energy. Okay, now the largest one should have been the one that basically had a noble gas configuration after you moved the first one. So which of these ions is going to be a +1 stable ion? Okay, and the one that's +1 and stable is lithium in column 1. Okay, our next periodic trend, electron affinity. Okay, this is the energy change when you add an electron to an atom. Okay, now, when you add an electron to an atom, take an atom plus an electron, okay, if it gives off energy, then this energy we say has a negative value. Okay, but if it's an atom that requires an electron and you have to add energy to it, then we say this energy here has a positive value to it. Okay, if it gives off energy, it likes the electron. If it requires the energy, it doesn't like it. Okay. When energy is given off, you will see a negative value for it listed in the table. Okay, the general trend. Well, which atoms, and if it likes it, that means it has a high electron affinity. Okay, so which atoms like to get an electron? Large ones or small ones? Okay, as you go left to right, electron affinity increases. Why? The small atoms like to gain the electrons. The big ones don't like to gain electrons. Okay? And going down, opposite trend. Because the atoms get bigger, the electron affinity will decrease. Okay? Now, noble gases. Be careful. Even though noble gases are the furthest on the right as you work your way across, these will not have a very high, these will basically have very low electron affinities. Why? They don't want to gain. Okay? So, the highest electron affinity is not in column 8, it's going to be in column 7. Okay? So, this element right here is going to be really high. Okay, so which of these will have the highest electron affinity? Okay, again, pause the video, find these on the periodic table. Okay, and the one that's going to gain it, or have the highest electron affinity, is going to be the smallest one that is not a noble gas, which is fluorine. Okay, which of these will have the lowest electron affinity? Again, find these, pause it. Okay, which one will it be? Argon. Why? This is a noble gas. Okay, if we didn't have a noble gas, you'd be looking for the largest atom. But the one that is, if it's a noble gas, it's always going to be the lowest electron affinity. Okay, so let's try a review. Multiple topics. Okay, which of these has the largest atomic radius? Pause. Okay, rubidium. Which of these will have the largest ionization energy? Pause it. Okay, largest ionization energy, you're looking for the smallest atom, which is going to be fluorine. Largest electron affinity. Pause it. Okay, largest electron affinity, you are looking for the smallest atom, which is going to be fluorine. Okay, and which one of these will have the smallest radius? Pause it. Okay, and it's fluorine. So, for our review, okay, where on the periodic table in general should you find the atom with the largest ionization energy?